Okay, geometry, lesson 19, construct and apply a sequence of rigid motions. We've done a little bit of this already, so this lesson has a ton of writing in it. So I need you guys to slow down and read through it. Take your time. There's going to be a little bit of construction, but I wanted to do the video this way just to make it more legible for you since it was a lot of reading. Okay, our opening. We have been using the idea of congruence already, but in a casual and unsystematic way. Congruence, we use the term equal measure a lot, but the technical term, the more formal term, is congruence. In grade 8, not necessarily for you, we introduced and experimented with concepts around congruence through physical models, transparencies, or geometry software. Excuse me. I doubt you did this. Transparencies, we would definitely do. Tracing paper, we would do a lot. And that's when we start introducing congruencies. Understand that a two-dimensional figure is congruent to another if the second can be obtained from the first by a sequence of rotations, reflections, and translations. Describe a sequence that exhibits the congruence between two congruent figures. Two-dimensional figures can be congruent to another if the second can be attained from the first. So if we draw a second, it's obtained from the first. Okay, they are exactly the same. With so many other concepts in high school geometry, congruence is familiar, but we now study it with greater precision and focus on the language in which we discuss it. We've discussed a little bit before, but vocabulary and language is very important in geometry because we need to use the same words to describe things to make sure that we're describing things correctly. Let us recall some facts related to congruence that appeared previously in this unit. First of all, we observed that rotations, translations, and reflections, and thus all rigid motions, preserve the lengths of segments and the measures of angles. This is important. When we do rigid motion transformations, we are preserving the lengths of segments and the measure of angles. We think of two segments, respectively angles, as the same in an important respect if they have the same length. So we think of two segments or an angle as the same if they have the same length for the segments or degree measure for the angles. So sameness of these objects relating to measure is well characterized by the existence of a rigid motion mapping one thing onto another. When we say mapping one thing onto another, I can take that same first triangle and that same second triangle, and what I want to do is pick this up and move it onto here to show that they are exactly the same. Defining congruence by means of rigid motions extends this notion of sameness to arbitrary figures while clarifying the meaning in an articulate way. We noted that a symmetry is a rigid motion that carries a figure to itself. So how do these facts about rigid motion and symmetry relate to congruence? We define two figures in the plane as congruent if there exists a finite composition of basic rigid motions that maps one figure onto another. Finite composition, so it's finite would be all-encompassing, everything about it, all pieces and parts. Lots of words, I told you. Thanks for being patient. If you need to take a break halfway through the video, please do. It might seem easy to equate two figures being congruent to having same size and same shape, okay? The phrase same size and same shape has intuitive meaning. That means you sort of understand it without really knowing you understand it. Intuitive meaning and helps to paint a mental picture, but it's not a definition, okay? It's something that we think we understand, but it's not really the definition. As in a court of law, to establish guilt is not enough to point out that the defendant looks like a sneaky, unsavory type. We need to point to exact pieces of evidence concerning the specific charges. It's also not enough that the defendant did something bad. It must be a violation of a specific law. Same size and same shape is on level of he looks like a sneaky bad guy who deserves to be in jail. So that's why just saying same size and same shape is not really how we're going to define congruence. It's a good starting place, but not a good finishing place. It's also not enough to say that they are alike in all respects except position on the plane. We are saying that there is some particular rigid motion that carries one to another. Almost always, when we use congruence as an explanation or proof, we need to refer to the rigid motion. To show that two figures are congruent, we only need to show that there is a transformation that maps one directly onto the other. However, once we know that there is a transformation, then we know that there are exactly many transformations, and it can be useful to consider more than one. We see this when discussing the symmetries of a figure. A symmetry is nothing other than congruence of an object with itself. A figure may have many different rigid motions that map it onto itself. For example, there are 6 different rigid motions that take one equilateral triangle with side length 1 to another such triangle. Remember equilateral? Oh, that was bad. Equilateral has all the same sides, and because all the same sides, the interior angles are always 60. Where was I? Whenever this occurs, it is because of asymmetry in the objects being compared. Lastly, we discussed the relationship between congruence and correspondence. This is important. We're going to be using this for the next 2 lessons. Congruence and correspondence. A correspondence between 2 figures is a function from the parts of one figure to the parts of another, with no requirements concerning the same measure or existence of rigid motions. Okay? I can talk about, 2 triangles that are not congruent and just compare. I can compare AB and DE without saying that they're equal, okay, segments. I can say that angle A is congruent to angle D. This is a squiggly line. But I don't have to say that anything else is congruent. I'm just talking correspondence, so I'm comparing things. If we have rigid motion T that takes one figure to another, then we have a correspondence between parts. For example, if the first figure contains segment AB, then the second includes corresponding segment transformation A, transformation B. This is function notation. We're going to need that in the future. But we do not need to have a congruence to have a correspondence. Okay, we can talk about things comparing to each other without them being congruent. We might list the parts of one figure and pair them with the parts of another. With 2 triangles, we might match vertex to vertex, which I did here. Then the sides and angles in the first have corresponding parts in the second. That means parts that match up, not necessarily the same measurement, but we can talk about them together. But being able to set up a correspondence like this does not mean that there is a rigid motion that produces it. The sides of the first might be paired with the sides of different length in the second. Correspondence in this sense is important in the triangle symmetry. Okay, let's go through some discussion. We now examine a figure being mapped onto another through a composition of rigid motions. Okay, to map triangle PQR to triangle XYZ, so PQR to triangle XYZ, we first rotate triangle PQR 120 degrees, okay, right there, about D. So rotate about D 120 degrees. Then reflect the image, reflect across segment EF, right here. So first we rotated it, remember counterclockwise, then we reflected it, and then we translated it. Finally translated along the given vector to obtain triangle XYZ. Since each transformation is a rigid motion, triangle PQR is congruent to, there's our symbol, is congruent to triangle XYZ. We use function notation to describe the composition of the rotation, reflection, and translation. Okay, it's pretty funny if we look. Remember PEMDAS, we always go the inside first. So triangle PQR, first we rotated it 120 degrees about D. Then we reflected it on segment EF. Then we translated it on vector V, and we got our new triangle. Okay, do the innermost first, and then go outward and outward. So let's draw and label a triangle PQR in the space below. You guys can do this on your own. Make your PQR different than my PQR, and it'll be great. Use your construction tools to apply each of the rigid motions we have studied to it in a sequence of your choice. Okay, this is where actual videoing would have been a good idea, but there was so much to read, I just didn't think it was a good idea. Hold on, use function notation to describe your chosen composition here. Label the resulting image as triangle XYZ, and then complete the following sentence. Okay, so first I'm going to draw and label PQR. So that's what I'm going to do first. Second, I'm going to rotate it. Okay, so I'm going to push pause and do those two things, if you could do those two things on your own. Okay, I don't have tools for an iPad, but here you see that I just rotated it about 90 degrees, I guesstimated, about point, let's call it F. All right, I'm going to push pause again, and this time I'm going to reflect it. Okay, I just reflected the triangle over segment AB, which works, and now I'm going to go ahead and translate it. Cool, I'm done. Let's go ahead and try to use function notation to say what we did. So I'm going to start at the beginning and put that in the center. So I have triangle PQR. The first thing I did was rotate it about point F, 90 degrees. And put some parentheses around that. Then I reflected it, cute little R, over segment AB, and then parentheses around that. And then I translated it. I don't think I named my ray. Nope. I translated it on vector V, and that gave me triangle CPQR VTS. Which really means that this shouldn't be vector V, let's call it, I don't know, W. Be easy to change it here. There we go. I didn't want to use the same letters for anything. All right, good job. Let's complete the sentence on the next slide. Okay, triangle PQR is congruent to triangle XYZ because rigid motion map point P to point X, but I didn't do X. What did I use? I used point T. Nope, I used V. So V, T, S. Rigid motions map segments onto segments of equal length. And angles onto angles of equal measure. Cool. Example 2. On a separate piece of paper, trace the series of figures in your composition, but do not include the center of rotation, a line of reflection, or the vector of applied translation. Swap papers with a partner and determine the composition of transformations your partner used. Use function notation. I'm going to give you some tracing paper, and I'd like you to bring them in tomorrow. Okay? So bring in your tracing paper. Let's see, I think that's it. Okay, in closing, this is what we learned today. Two figures in the plane are said to be congruent if there exists a finite composition of basic rigid motions that maps one figure onto another. To notate composition functions, the innermost function transformation is performed first and the outermost last. Good work today.